In our last lecture, we had considered at first the geometric transformations, where we had shown the affine transformation matrix, and that we said that one can do translation, rotation and scaling using the affine transformation matrix which we had defined in the last class. And there we had said that if an image undergoes rotation by an angle other than 90 degree, or if the image undergoes some scaling, that's to say a magnification or some reduction by a real factor, then the transformed image that we get, there the pixels do not fall on the integral grid which we had originally defined. And that way we had said that there is a need to interpolate the image first, so that from the set of samples we can get the continuous image function, or rather we can approximate a continuous image function, and thereafter there is a need to resample the image. Then we had also considered some of the interpolating functions, and in that we had started with the definition of the B-spline functions, and we saw the nature of the 0th order B-spline function, which I had shown to be a to be like a pulse function, or rather the sample and hold type of function which we had defined, and that we had said that by a shift of origin it can be made to act as a nearest neighbor function. So you remember that the function which we had got, okay, for interpolation was that over the considering the central pixel, it was like this, that if this was the central pixel, and if this is 1 pixel on this side, this is 1 pixel on the other side, that is 1 pixel on the right and 1 pixel on the left. So this I am calling as pixel 0, this is +1, this is -1. So 1 pixel to the left, 1 pixel to the right, and the function which we had got was, that was covering the range from -half to +half, and this was our interpolating function which we called as the nearest neighbor. So we had only seen the 0th order interpolation, and today we are going to see the nature of some higher order interpolating functions using the splines. Now firstly, that this kind of an interpolating function which we said is nearest neighbor, okay. Now one major property of this nearest neighbor function is that it involves only, it spans, this interpolating function spans only for interpixel distance equal to unity, just this much, because it is ranging from -half to +half, okay. So the interpixel distance is unity, but really speaking, there are some interpolating functions where instead of taking just the instead of taking it over only 1 interpixel distance, we need to take it over more than 1 interpixel distances. So that means to say that we need to have a little bit different kind of interpolation functions, so that rather than considering only the nearest neighbor, we consider the effect of just a few neighbors. Obviously the closest neighbors will have more contributions, but little bit of more contributions from other closer neighbors also, okay. Of course, as I talked in the last class, that basically B-spline functions, they have the property that it covers only a finite supporting range, okay. Now the first order, the 0th order B-spline function we had written as B0, okay, where B0 stands for the zeroth order interpolation. We had substituted n equal to 0 in our formula for the B-spline, or rather our definition for the B-spline function, and by substituting n is equal to 0 we have got B0, which is of this nature, right? Now if we substitute n equal to 1 in that function, okay, then what nature of function do we expect? Okay, I mean, rather than applying the applying n equal to 1 directly into our definition of B-spline function, which we had shown in the last class, okay, it may be convenient for us to write the higher order B-spline interpolation as convolutions of this convolution operation over this B0. That means to say that if we are talking of a B-spline function with n equal to 1, okay, then what we are getting is B1, the function B1, and the function B1 can be obtained as convolution of B0 with B0, okay. If we convolve B0 with B0, we get the function B1, okay, which is the first order spline interpolation. If we want B2, then what we simply do is B0 convolution with B0, and with this result we convolve another B0, thereby we get B2, okay. Like this it is possible to get the higher order higher order interpolating functions. So if you convolve the function B0 with B0, okay, what nature of function do you get? Correct. Somebody has given the correct answer, that it gives rise to a triangular function. And can you tell me that how many pixels does that function cover? How many pixels will that triangular function cover? What will be the range of that triangular function? Obviously its maximum value will be near 0, okay, and what will be its value at +1 and -1? I mean, just at that point it will drop down to 0. So that means to say that our function will be of this nature. If this is 2, 3, etc., I mean beyond +1 and beyond -1 on this side, okay, the function value is 0, but between -1 to +1 it is having a function of this nature. So this is the nature of B1, okay, which is the first order spline interpolation, or rather what can we call? We can call it as a linear interpolation. So this we will call as a linear interpolation. B0 was the nearest neighbor interpolation. Whereas B1 is the linear interpolation. So the question which I was asking is that how many pixels does this function cover? It basically covers 3 pixels. The pixel 0, the pixel at +1 distance, the pixel at -1 distance. Of course its contribution just drops down to 0 over here, but the total span, okay, or rather the total coverage of this function is from -1 to +1, which means to say an interpixel distance equal to 2, or rather it covers 3 pixels, -1, 0 and +1, okay. What do we get? What nature of function do we get for B2? Just this function we need to interpolate, I mean we need to convolve once again with this B0 function. So what we get is a quadratic interpolation, and that covers, instead of 3 pixels over here, it covers 5 pixels. No, not 5, sorry, it covers 4 pixels. It just covers 4 pixels when it is a function B3, but 4 pixels of course does not make it symmetrical in our case. So instead of considering B2, what we use many a times is the function B3. And in B3 what we get is that it will be convolution of B0 with B0 with B0 with B0 once again. So that is a 4 times convolution of B0 will give rise to the function B3, and that should span an interpixel distance of 5, okay, and its nature is like this. Here we have -2, -1, 0, +1, +2, and the nature of the function is of this, is like this. At -2 it drops down to 0, again symmetrically at +2 it drops down to 0, and this function B3 is called as the cubic B-spline interpolation. So B0 is only doing a nearest neighbor on this central pixel, a nearest neighbor algorithmic results. The linear interpolation is considering the range from -1 to +1, okay, maximum value at 0, and dropping down to -1, dropping down to 0 at -1 and +1, and then comes the cubic function, okay, which we have shown over here, okay. In this case the total span is 1, 2, 3, 4, 5 pixels, okay, or rather interpixel distance of 1, 2, 3, 4, correct. Now which one should we adopt, whether the nearest neighbor or the linear interpolation or the cubic interpolation? This is what we have to decide. So we have to think of a comparison between these 3 types of interpolating functions. Now obviously nearest neighbor kind of interpolation is quite simple to implement. It does not involve any computation, okay. What you need to do is simply to find out the intensity value of the nearest neighbor. I mean, considering a 2-dimensional grid, you have to just be on the lookout for the nearest neighbor pixel, and whatever intensity value we have there, okay, the point under consideration, okay, will get that intensity value simply. Now the nearest neighbor, now basically whenever we are doing an interpolation of this nature, all that we are doing is we are taking a locus filtering. We are performing a locus filtering on the image, okay, and this nearest neighbor kind of interpolation, this gives a very good performance in the pass band, but its stop band performance, okay, for the low pass filter is bad, because obviously what happens is wherever there are sharp transitions in the intensity, those sharp transitions in intensity will be retained in the nearest neighbor algorithm also. Whereas in the case of linear interpolation, what you are doing is that you are finding out the intensity values at other pixels according to this linear interpolation formula. Now in that, what we have is our passband performance is little poorer as compared to the nearest neighbor, but the stop band performance is better, okay. And in the case of cubic interpolation, the stop band performance, okay, is furthermore improved, okay. So obviously the performance depends upon what quality of image do we have? Okay, if we have more of high frequency components, okay, if the image data itself is a high frequency data, then doing a nearest neighbor interpolation will be better. But if the image is not having high frequency components, okay, in its data, then it will be worth doing the linear interpolation or cubic B-spline interpolations. Now there have been a number of applications, okay, for this linear and cubic B-spline interpolation, and I will give you the references of some of those applications. Actually, let us first list out that what kind of applications do we have with this interpolating functions. Now, as I said in the last class, that very often we need to do some geometrical corrections on the satellite images, because the original satellite image is produced on a distorted raster, and out of that we have to get get the image on a corrected raster, and in order to do that correction we need this interpolation and resampling. So the first application we can say geometric corrections of satellite images. Now apart from geometric corrections, okay, many a times we need to compare or match the images, okay, from different sensors, okay, different satellite sensors. We need to compare the images, and those images are actually taken at different resolutions. So maybe that we have a sensor 1, sensor 2 and sensor 3, and sensor 1, 2 and 3, they have captured the images at different resolutions. Now if we want to match the image of sensor 1 with that of sensor 2, okay, we cannot do a pixel to pixel level of matching, okay, on the original image. So what we need to do is to do interpolation and then resampling, so that all the different images, okay, which are there in different resolutions can be resampled to a common resolution on the basis of which the 3 images or 3 or 4 images can be properly matched or registered. That problem is called as image registration. So I should say the second application as registration of images from different sensors. Images obtained from different sensors. This has got applications in defense also, because one can take the images from various kind of sensors and try to match those images, where this interpolation and resampling is very much used. The third major application of interpolating function is in medical images. In medical images, okay, very often we need to have a better display, okay, of the images from X-ray, ultrasonography and other radiological images, okay, and in order to have a better display of medical images, okay, one needs to do this kind of interpolation and resampling. Now obviously, as I told you in the first class itself, please remember that interpolation does not increase the information content of the image. Okay. So we are not increasing the information content, but we are only making the image appearance smoother, okay, and visually we can give a better effect by interpolating and then resampling on a finer grid, okay, and that is what many a times people need for the display of medical images, okay. Now like this there are several applications for interpolating functions. Now one major application of interpolating function is that wherever we need to do any magnification or reduction of image. So magnification and reduction, actually we very often use the terms as enlargement, and the opposite of that is reduction, but I have seen that some literatures are using terms magnification and minification. So if we are talking of magnification, we can also do minification using this kind of interpolating techniques, okay. So magnification and minification, and typically we can do such magnification and minification by a real factor. Okay. Now let us study the different ways whereby we can magnify or minify the images. Let us study some of the image magnification techniques. Now supposing we have got a 256 by 256 image, and let us say that we want to magnify this image so that it can occupy a grid space of 512 by 512 pixels, okay. So we would like to magnify this image by a factor 2 in each direction, or rather its total number of pixels will become 4 times, because 256 by 256 pixels makes it 64 kilobytes, and 512 by 512 makes it 256 kilobytes. Now in what manner can we magnify this image? Forget about interpolation, okay. Do you think that there can be any simpler technique to magnify this image? Any simpler technique to magnify? Yes, somebody has given the answer that we can magnify this image easily by replicating the pixel, or rather putting the same pixel in 4 different places. Like if this is 1 pixel, okay, what he has suggested is that in the magnified image he will be putting this pixel intensity value in all these 4 pixels. If this pixel is having intensity value equal to A, his suggestion is that in the enlarged image this 2 by 2 space, okay, will be filled up with intensity A, and then if the next pixel is having an intensity value B, that will be written as follows. All the 2 by 2 pixels over here will be written as BB. If this is the pixel C, then pixel having intensity C, then this will be written as C, 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 that is to say this 2 by 2 will be filled up with C. Then here all the 4 pixels will be filled up with D. So we had a 2 by 2 image space over here, and this is magnified into a 4 by 4 image space by simple what is called as pixel replication. We are just replicating the pixels. So that is quite a simple technique, okay. But I mean simple in the sense that we don't require any computation, okay, to find out the intensity values at all these pixels. But obviously all the artifacts of the image, okay, that is still retained over here. Means wherever there are sudden sharp transitions in the intensity, okay, those will be preserved even here also, okay. And moreover the image will appear like a more of a box structure. That is to say, this pixel A you are now replicating into 4 pixel. This 1 pixel is being replicated into 4. So that effect also will be there. Now rather than doing the pixel replication, we can also do the interpolation. We can also find out the intensities of other pixels by means of interpolation. Now obviously this kind of a pixel replication we can do only when we want to do the enlargement by some integer factor. If I say that instead of magnifying this image from 512 by 512 pixel space to from 256 by 256 pixel space to a 512 by 512 space, if instead of that I say that I want a magnification from 256 by 256 pixel space to say 320 by 320 pixel space, what do we do? Obviously we can't do the pixel replication. We have to do interpolation only, correct? So in that in interpolation technique we have already learnt of the nearest neighbor. So we can do a nearest neighbor interpolation, or we can do a linear interpolation, actually this linear interpolation we have to do in x direction as well as in y direction. So really what we get is a bilinear interpolation. And the third is interpolation using cubic B-spline. Generally functions, B-spline functions of order higher than n equal to 3 is generally not used, because it is computationally more involved and it covers the function, the spline function covers a large number of pixels, okay. So that is why a lot of computations are involved, and it is found that cubic B-spline functions itself, they give a reasonably good performance, okay. Whereas for simpler applications linear interpolations are quite commonly used. Now in the case of linear interpolation, let us say that we know the value of a function, value of an intensity function at some point k. At some point k it is known, and also the intensity function is known at the point k plus 1. And our objective is to find or estimate the function value at the point k plus r, where r lies between 0 and 1. So we are considering the intensity value at point k plus r, where r is a real factor. We know f of k and we know f of k plus 1. Okay. Now in the linear interpolation, if we want to do linear interpolation, can anybody tell me, okay, that what should be the relationship between fk plus r, fk and fk plus 1? Actually we will get, by simplification we will get, this becomes r times fk plus 1 minus r times f of k plus 1. Okay. So if k plus 1 is known, if fk plus 1 is known to us, if fk is known to us, then given some r, okay, we can find out the intensity value at point fk plus r using this formula. Okay. Have I done it correctly? Or any? Pardon?
Spline interpolation, not in case of linear interpolation.
This is a linear interpolation. This is a spline interpolation only, but with n equal to 1. Okay?
I mean, it's not a general linear interpolation.
The general linear interpolation means obviously, we are considering this one is n equal to 0, this is n equal to 1, and this is n equal to 3. Okay, and general interpolation means with n, that we are not considering. This is for linear interpolation. This formula, this expression is for linear interpolation.
Linear spline interpolation.
Linear spline interpolation, correct. Yes, because I find some mistake in this relationship. This should be fk plus r. I mean, if I substitute r equal to 0, then obviously I am not getting the relationship. Then I am getting fk equal to fk plus 1, which is not correct. So I should have got, this becomes 1 minus r into fk, and this one is r times fk plus 1. Is this correct now? Just substitute r equal to 0 in this expression. You get f of k on this side, f of k on this side also. If you substitute r equal to 1, you get f of k plus 1 on this side, f of k plus 1 on the other side also. So this is the linear spline interpolation relationship. Okay, and this we have to do on both x as well as y directions. Okay, if we do that, then we can find out the pixel value anywhere in the real space. Okay, means from the image we have got the intensity values only on the grid intersections, whereas using the linear interpolation function we can find out the intensity values at any in between points in the real space. And if we can do that, then it is absolutely up to us that where do we resample the image. Because after interpolation we can resample it according to our defined grid. Anybody having any difficulties on this? Okay. Now just I would like to tell a few words more on this cubic B-spline interpolation function. Now for the cubic B-spline interpolation, the relations can be defined like this. Actually, what is the coverage of cubic B-spline interpolation? 5 pixels. That means to say from -2 to +2. So it covers -2, -1, 0, +1, +2. Okay. And of course it is symmetric. So that means to say that if we are knowing the nature of the function from 0 to 2, okay, we can also know the nature of the function from 0 to -2 also. Is that correct? Now from 0 to 2, the function can be closely approximated like this. F of x, if f of x is the real function which we are interpolating, then f of x is given by x cubed by 2 minus x square plus 4 by 6. This is what we get for the range of 0 and 1. So this is when x lies between 0 and 1, okay, fx takes this form, and when x is between 1 and 2, it takes a form like this. Fx is equal to minus x cubed by 6 plus x square minus 2x plus 8 by 6. So this is the cubic B-spline relationship. So using this expression, okay, we can interpolate the pixel anywhere on the real grid. So the same thing, that if our pixels are defined on the integer grid intersections, then taking any pixel in between, we can know its intensity value by applying this relationship. Okay, and of course the intensity value that we get, okay, is a contribution of totally 5 neighbors. Is that correct? Now just a few references. On the image interpolation and resampling, some very useful references are this. The first one is by J. A. Parker, R. V. Kenium and D. E. Troxel. It's comparison of interpolating methods for image resampling. It appeared on the IEEE Transactions on Medical Imaging, volume MI2, number 1, March 1983, and the page numbers are 31 to 39. The second reference is by H. S. Howe and H. C. Andrews. The title is Cubic Splines for Image Interpolation and Digital Filtering. It appeared on IEEE Transactions on Acoustics, Speech and Signal Processing, ASSP, volume 26, number 6, December 1978, page numbers 508 to 517. Number 3 reference, by R. G. Keyes, Cubic Convolution Interpolation for Digital Image Processing. This appeared on IEEE Transactions on Acoustics, Speech and Signal Processing, volume 29, number 6, December 1981, page numbers 1153 to 1160. So I am keeping this for a little more time so that you can take down these references. Okay. So let me read it out once more. First one, J. A. Parker, R. V. Kenium and D. E. Troxell. Comparison of interpolating methods for image resampling, IEEE transactions on medical imaging, volume MI2, number 1, March 1983, page numbers 31 to 39. The second reference is by H. S. Howe and H. C. Andrews. The paper is Cubic Splines for Image Interpolation and Digital Filtering. It appeared on the IEEE Transactions on Acoustic Speech and Signal Processing, that is ASSP, volume 26, number 6, December 1978, page numbers 508 to 517. Third reference is by R. G. Keyes, Cubic Convolution Interpolation for Digital Image Processing, IEEE Transactions on ASSP, volume 29, number 6, December 1981, page numbers 1153 to 1160. Now, let us discuss some things which we will require in our next lecture. Basically, before going into the next lecture, where I want to cover the perspective transformations of images, before that I would like to cover the basic transformations in imaging geometry. Now, let us consider a three-dimensional coordinate system. A three-dimensional x, y, z coordinate system which we have taken, and let us say that a point coordinate is denoted by x, y, z. Okay. Now, in order to represent the basic transformations, okay, what we need to do is to have a unified mathematical representation, and that representation we will do in this form. Where that is a vector V star, okay, will be written as the product of matrix A and matrix V, okay, where the vector V is a vector, okay, where V is a column vector containing the original coordinates. Now, the original coordinates, as I already said, is capital X, capital Y, capital Z. Okay. But in this column vector V, okay, I am introducing one more element. So, I am making it a 4-element column vector, and the fourth element which I am introducing is a unity. So my column vector V is now defined like this. Its elements are capital X, capital Y, capital Z, all three of which define the coordinates X, Y, Z, and in addition I have yet another element, the fourth element, which is equal to unity. So this is the original coordinate column vector, and then A is a 4 by 4 matrix which indicates the geometric transformations. Okay, and this V star, this is yet another column vector, okay, having 4 elements, and this will denote the transformed coordinates. Means after undergoing the geometric transformation, its coordinates will be X star, Y star, Z star, 1. So this is the column vector V star here. Now this transformation matrix, so this is the basic relationship, that the column vector V star will be a product of the 4 by 4 transformation matrix and the 4-element column vector indicating the original coordinates, okay, and this will define our basic transformation. So in the last class you had seen that we were defining the affine transformation, okay, as a summation of the product of a 2 by 2 matrix and a column vector plus yet another column vector indicating the translation. Whereas in this case, translation, rotation, scaling, and rotation not only in rotation is not only within a plane, but rotation could be in about any one of the 3 axes, okay. All these things we can represent within this transformation A. So now to take the simplest case, okay, if we have translation, let us consider the case of a translation by an amount x0, y0, z0. So x0 is the translation in x direction, y0 is the translation in y direction, z0 is the translation in z direction. So if we have that, then can you tell me that what will be the nature of this A matrix?
1, 0, 0, x 0.
1, 0, 0 in x naught, yes. So this transformation matrix A I will now call as a matrix T, and its elements will be, yes, 1, 0, 0, x naught, correct. The next row,
0, 1,
y naught. The next row, 0, 0, 1, z naught. And the last, yes, 0, 0, 0, 1. So if the translation amounts x naught, y naught and z naught, all of them are zeros, then this matrix A becomes a identity matrix. So this transformation matrix A, which we are now calling as T because it indicates the translation, is nothing but an identity matrix except for these 3 elements, okay, x naught, y naught and z naught, which indicate the translation, okay. Now let us consider the case of scaling. if we have scaling, then we will define that transformation matrix by S, okay, and taking a general case that the scalings could be different in x, y and z direction. So taking the scaling in x direction to be Sx, scaling in y direction to be Sy, and the scaling in z direction to be Sz, then what is going to be my transformation matrix? S Sx 0, 0, 0. That is the first row. The second row is 0, Sy 0, 0. The third row is Sz 0, and the last one is 0, 0, 0, 1. So this is our scale. What about rotation with respect to the z-axis? This is, supposing this is y, this is x, this is z. We have a point over here, okay, which is rotating by an angle theta. Or if we consider the rotation around y-axis, the angle beta will be shown in this way. And if there is a rotation around x-axis, then we will define the angle as alpha, which is positive in this direction. So if there is a rotation in the theta direction, that is to say rotation about z-axis, in that case the transformation matrix which we have, the transformation matrix A, will then be written as a matrix R theta, okay. And can you tell me what will be the elements of this matrix R theta?
Cos theta.
Cos theta
Minus sin theta.
It will be sin theta in this element. Sin theta 0, 0. This element will be minus sin theta cos theta 0, 0. This will be 0, 0, 1, 0. This will be 0, 0, 0, 1. So this is rotation about z-axis, that is to say r theta. Very similarly, r alpha can be written as 1, 0, 0, 0, 0 cos alpha sin alpha 0, 0 minus sin alpha cos alpha 0, 0, 0, 0, 1. This is R alpha, that is to say rotation with respect to the x-axis. We are taking a three-dimensional point, and a three-dimensional point can undergo translation in all these three directions, x, y, z. It can undergo scaling, it can undergo rotation about z, about y, about x. So this is rotation about x direction. And now the rotation about the y direction, that is r beta, can be written as, it is cos beta 0 minus sin beta 0. This row is 0, 1, 0, 0. This is sin beta 0 cos beta 0. This is 0, 0, 0, 1. So this is the transformation matrix R beta, indicating rotation about y axis. Okay. Now very often we need to have all these operations, or rather very often we find that not only an object has undergone translation, but it has undergone rotation in, around z axis, around y axis, around x axis. Many of these things can happen together. Let us say that an object has undergone a translation, it has undergone some scaling, and it has also undergone a rotation about the z axis. So an object has undergone, what I said is, an object has undergone translation, it has undergone scaling, and it has undergone rotation about z axis. So if all three of these have taken place, okay, and still if I want to represent my transformed coordinates, okay, written in the form of the V star column vector as a product of A column vector and V column vector, then what do we do? How do we get this in transformation matrix A? This transformation matrix A I will get as concatenation of all these different basic transformation matrices. I said that it has undergone translation. So I should first say P multiplication with V, okay, and then on this we have considered a scaling, and on this result we have considered R theta. So together this will compose our A matrix, the transformation matrix A, or rather this will be the total operation, rather our V star column vector will be this, so that our A can be written as R theta S T, a product of all these three, or rather the concatenation of all these three matrices. Any question? So with this basic transformation, basic imaging transformations in three-dimensional coordinates, we will go over to our next topic of discussion, which is perspective projections and its transformations.
If the rotation is about some arbitrary point,
if the rotation is about some arbitrary point, then obviously we can first translate the coordinates to that particular point and then do the rotation. So it will be a combination of translation and rotation. Any other question? Thank you.